Part 2 on JMESPath. Coming up, we're going to look at things called filter projections, a MultiSelect List and a MultiSelect Hash, two types of multi-select, and this is going to mark our shift towards creating structures in the result as opposed to simply parsing the data we're querying. We're going to clarify what we mean by hash. We're going to look at a complaint from the angry face about flattened projections or flatteners, and we're going to point out this distinction between projections being picky and when it comes to multi-select queries beginning with M, they like to mirror the structure and they will put in null when they don't find anything, but that'll make sense, that distinction between projections being picky and a mirrored structure in due course. Why is Dr. Ritchie there? I'm not sure. Worked on the C programming language at Bell Labs. Dennis Ritchie. Filter projections. Up to this point we've looked at list and slice projections, object projections and flatten projections, which are helpful for compound projections. Evaluating the right hand side of a projection is a basic type of filter, so in a way we've already looked at filters. If the result of the expression evaluated against an individual element results in null, then the element is excluded from the final result. A filter projection allows you to filter the left-hand side of the projection before evaluating the right-hand side. So a question might be, if we already have a basic filter, why do we need another? So what we want to be looking for is the fact that there's a novel advantage to this. Clearly there must be an advantage to being able to filter the left-hand side before evaluating the right-hand side. So let's keep that in mind. We'll bracket that for now. A filter projection allows you to filter the left-hand side of the projection before evaluating the right-hand side. For example, let's say we have a list of machines. Each has a name and a state. Okay, so a bunch of properties. Instead of people, we've got machines here. We'd like the name of all machines that are running. So straight away, let's think, would a normal projection, the ones we've already looked at, be able to deal with that? Presumably each machine is a hodgepodge of properties, so it's a collection. It's enclosed within, all the properties are enclosed within curly brackets, and it's key, colon, value, comma, key, colon, value, where one of the keys is name and one of the keys is state. So could we use a normal projection with that? We could have the left hand side be machine, the right hand side could be name. Oh, but we want the names of all, but how would we make sure the machines are running? Okay, what if we had the right hand side be the state? But that would tell us what the state is. It wouldn't select out only the states that are running, it would just say here's a list of all the states of the machines. Okay, well what if we had the left, with a normal projection, what if we had the left hand side be the name and the right hand side to be the state? Does that work? The left hand side be the name, but there all we're doing is we're evaluating the name key and evaluating the state key. We're not saying the state has to be running. So if you think back to the classic list projection example we've been looking at, James, Jacob and Jaden, we take the first names, but there's never any question of what the name would be. We don't say I'm only interested in people whose first name is Jam, or so there's no selection there. So there is a difference here. With a filter projection, we're selecting based on the value. So we're going to look at some pseudocode now. Result equals empty square brackets. So overall, this isn't we've got a condition here. So if, and then we've got the condition, machine is set if it's equal to running, result dot insert at end and applied to what's in these rounded brackets here, and then we say return result, so it's an if return, so that you can see that overarching structure there. And it's our method there. So a filter projection can be used to accomplish this. So here, there we go, we've got a list of machines, and each machine is a collection, so an associative array. Question mark state equals stopped dot name, and then we would get back this result, just B. Let's break that down. So there's the structure, and we of course have seen that a lot, just the structure being field and then something in square brackets to the right of that. But now we're using a question mark to say I'm about to express a filter. There's a question mark just tucked within the opening square bracket, and we're saying I'm only interested in this value of the field being state and the value being stopped. We're not interested in running or terminated, and it follows the principle of the more specific to the right. So we're not saying stopped has to be equal to state, there is a sort of direction to it. Question marks, of course, are always also used for the query string in a URL. Why double equals? Well, in programming, the equal sign is used for equality and copying. For example, if x equals 0 means if x is equal to 0. However, x equals 0 means copy the value 0 into that variable x. Double equals sign means equal to c. For example, if x equals 0 means if x is equal to 0. And they say the unusual use causes many errors in C. I don't think so. That's from PC Mag. I don't think that's a very good explanation, because they say this here, if x equals 0, means if x is equal to 0, and then using the double equals sign here means x is equal to 0. So they've translated it into English, where the English is the same for each one. So I think that's a bad explanation. So there's Dennis Ritchie, and if we go to his textbook on C, second edition, not just his, the double equal sign is the C notation for is equal to. This symbol is used to distinguish the equality test from the single single equals that C uses for assignment. A word of caution, newcomers to C occasionally write equals when they mean equals equals. So let's explore that. Here's Dennis Ritchie getting the, I think it's the US National Medal of Technology from US President Bill Clinton. That's 1998. Here he is at Bell Labs working on something to do with Unix probably, and it wasn't a very good building there. The walls were actually double insulated. There was a cavity in between them, and his supervisor came to him, I think in the 70s, and said, look Richie, we're chasing up with Harvard trying to see if we can find your PhD. And Richie just sort of went around the question and passed it off and said, I'll get back to you another day. And his supervisor had to come in the next day and said, come on, is anything true? I've been speaking to people at Harvard and I can't find your thesis for your PhD. And things just got more and more heated. I'm going to ask you questions every day. I don't like testing you, he eventually had to say. And he got so fed up that there was a pole nearby, a tall pole used for opening the high-up windows in the office, and he actually threw it across the room at Ritchie, and it went into the wall behind him and made a hole, something almost like a spear going through the two layers of the wall like that. And ever since, Ritchie associated that shape, the double equals, with questioning and checking and testing. Not a true story, but the double equals sign, that's it's a test. That's about, you're essentially giving a question when you use that in C. You're asking, is the argument on the left the same as the one on the right? And the suggestion here is that most people tend to not use that double equal sign because that's the strange one, isn't it? Not just a 1 equals, when actually they should be using that question sign. As for 1 equals, we call that the assignment operator. So let's try not to give an explanation where we just say one of them is an equal sign with that PCMag explanation. That's the assignment operator. You're setting the variable to that value. Whereas here, with double equals in context here, it's called the equality test. So whenever you're putting a condition next to an if, saying if x, is it equal to y? It's a question. So many questions. Print such and such. Whereas up here, this is the assignment operator. So we're saying x is equal to such and such. Y is equal to. Here's the assignment operator. Assignment is done with the single equal sign. It should never be confused with the equality test operator. So that's why here in a filter projection we use a double equal sign. We're asking, is state equal to running? And we ask it about this first element in the array. We ask it about this second element. We ask it about this third element. So this is the equality test. And of course there are 2 elements in this array which are running. This is still a projection. It has a left-hand side and a right-hand side. The left-hand side being machines. Is that right? I think that, yes, it's a filter projection after all. It's called a filter projection. So the left-hand side gets to work, and then the right-hand side is not the filter. The right-hand side is still name, but of course things have already been cut down before we get to name. Only to have running. So what's interesting about this, of course, is that if we look at the result, we're not extracting the state field. Yet state is in square brackets. So we're pinpointing a particular attribute of machines, but ultimately what we want from them is their name. We don't want actually to put their state in the result. And that's the essence of why these have a capability that you don't have with a normal projection, filter projections. Yep, we've got an array here overall. Fine. The tutorial says try changing running to stopped in the example above, and hopefully that will get the one machine which has a state of stopped. You can also remove the .name at the end of the expression if you just want the entire JSON object of each machine that has the specified state. So let's put state, is it the equality test stopped, and then we get back the name of the only machine that is stopped. We remove the .name, and it's still stopped, and now we get name B, state stopped. We just get that whole object printed in the result. So let's just think about this for a minute. Could we have used any other tools for this? Because now we've removed the .name at the end, it's not obviously a projection anymore. This is our classic example of a list projection that we looked at, people.first. Couldn't we have used something like that here? No, because with people.first, we're printing the value of the first key, James, Jacob, Jaden, and what we're after here is a distinction between how we select the machines we're interested in and what about the machines we print. So just because we're interested in their state doesn't mean I want to print their state, I want their name. And it's that distinction between what we want and what we want to print that we can't get with a projection, with a plain old projection. Could we have used something like this? Remember that classic example of an object projection with ops, a plain asterisk and then .numargs. And remember, numargs was a value right within the curly brackets. There was no array in sight here. Obviously we'd change numargs to, well, what would we change it to? Name, state. But my point is, would that general structure be useful here? We could do machines dot asterisk dot. No, well, we couldn't. Why? Because machines is an array. The value of machines is an array, and so this object projection is not appropriate here. But for the sake of argument, let's suppose that the square brackets that we see in this data were curly brackets. Could we use machines.star dot stopped? No, num-args was a key, so you can't just put star dot and then name a value. Okay, but could we put machines.star.state? Well, yeah, but then we'd just get a list of all the states. We wouldn't have that filtering. Could we put machines.star.name? Yes, but then we'd just get a list of the names. So you can see that even if we assume that this was an object, which it isn't, it's machines and then the value is an array, it's still not appropriate. What about something like this, where we had that compound projection? Could we not use that here? We could do machines and then a star in square brackets dot name. No, because name's value isn't an array, so that wouldn't really work there. Yeah, instances has to have an array. We need another key that has a value which is an array, so that wouldn't work there. A filter expression is defined for an array and has the general form left hand side and then that question mark tucked within the square brackets, expression, comparator, and then expression, so bigger than, smaller than. The filter expression specification details exactly what comparators are available and how they work, but the standard comparators are supported, i.e. the equality test, exclamation mark equals, which means not equal to, less than or equal to, greater than or equal to. Okay, now we're going to move on to pipe expressions, but first just remind yourself of something we've looked at so far. There's the classic example of a list projection, people and then a asterisk in square brackets dot first, and we've got each person, each hodgepodge of properties is an associative array. The associative arrays are separated by commas, and we were able to tinker with this to make it so that we put, yeah, so that's an array. What I did, I put a 0 in the square brackets in the query instead of an asterisk, and that meant that we just got James back. Why? Because we're looking only at the 0th element in the people array. And the right hand side of the projection is ensuring that we only look for whatever's next to the first key. So let's keep that in mind now that we look at pipe expressions, because something puzzles me here. Pipe expressions. Projections are an important concept in JMESPath. However, there are times when projection semantics are not what you want. A common scenario is when you want to operate on the result of a projection rather than projecting an expression onto each element in the array. The expression people star first will give you an array containing the first names of everyone in the people array. True. What if you wanted the first element in that list? The people list. Okay. And I think I've just shown how to get it. I'm not sure. They say if you tried people star dot first and then 0 in square brackets, well, we can see that that wouldn't work. Remember that principle, the index is internal, so it doesn't focus on the 0th first key, it focuses on the value next to first and the 0th element within that. So you should see that that won't work. First doesn't have an array as its value. Hopefully you can see that. So if you tried that, then you just evaluate first 0 for each element in the people array, and because indexing is not defined for strings, that final result would just be an empty array, so that wouldn't work. To accomplish that desired result, you can use a pipe expression. Expression this vertical line and then some expression on the right hand side of it to indicate that a projection must stop. This is shown in the example above. So that bit of text was a bit confusing to me, so I was saying, let's go over it again. The expression people star first will give you an array containing the first names of everyone. What if you wanted the first element? They were pointing out that if you did first 0, that wouldn't work, and indexing is not defined for strings. So you desire one name. People might think that putting first 0 would work. Why? Because 0 is an index expression and it says we only want the first item. We only want the first name. That's their reasoning. But we know, because of this index's internal principle, that that's why that won't work. And the second reason it won't work is that indexing is not defined for strings. Okay, index expressions locate elements within an array, and we've got a JSON object literal. But like I said, this works. Maybe it's a fluke that it works on a tutorial. I don't know, just putting 0 in square brackets to get the 0th element. But anyway, the point is enter pipe expressions. And another complaint. Okay, I thought we did have projections for objects. Okay, so I'm thinking now, well, if the reason that didn't work when we put first 0 is because indexing is not defined for strings, right? And if we look at the JSON that we're trying to query, if we look at the JSON we're trying to query, it's well, James, his bunch of properties, including his first name, his last name. James is an object. His properties are bunched together in curly brackets. Therefore, any sort of tool that's used for lists won't work for that. So that makes me think, well, hold on. We do have a tool for working on objects, and that is object projections. So here we have this ops object, right? The value is a bunch of properties in curly brackets. Okay, so function A value comma function B comma. That is the same as the bundle of properties making up James, as it were. So why can't we do people dot star dot first, which is analogous to that, right? People dot star dot first, but do it on that. The reason that won't work, I think, is that people's value is an array. So to use this tool, this object projection, it's got to be the thing on the left hand side of the asterisk has to have as its value an object, something in curly brackets, and unfortunately the value of people is an array. So yeah, that's why that won't work. They're sealed within square brackets, the people array. Okay. Yeah, and that's an important point. The asterisk in an object projection, it's not just being a wildcard, it's actually saying this is an object projection. The value of ops, or whatever's on the left of the asterisk, is an object, is a thing in curly brackets. Yeah. So yeah, I've tried putting a 1 there instead of an asterisk, and the result is unchanged. So that's not what's happening there. It's not like the asterisk isn't saying you can swap me out for a number. No. So on to pipes. Here we go. Here's the general syntax: expression to the left and to the right. And in English, that vertical bar is saying take the output from the left-hand expression and use it as input, that should say, as input for the right-hand expression. So we're feeding it into that expression on the right-hand side of the bar. So there's our classic list projection, but now we're going to feed it in to the right. People sometimes say even pipe it in to the right. So that's a projection. What do projections result in? Objects? No, arrays. And what can we use to query arrays? Index expressions. And that's what we do. We apply an index expression, 0 in square brackets, to the output. Okay, so let's look at this data. We've got it's an object overall. We've got those curly brackets at the top and the bottom, and the value of people is an array. There's a closing square bracket, and there are the elements within it. The value of foo is an object, so there's a difference between people and foo. Now let's fill those out. Those 3 elements, or 4 elements going up to third. Okay. So when we apply the asterisk, we're interested in all the elements of people. Then we project that we apply the right hand side first. And the result of that projection is that array. Projections result in an array, James, Jacob, Jaden in square brackets. 0 first and second. We apply that index expression which focuses on the 0 if only, and execute. And so the result should be James. Lovely. In the example above, the right hand side of the list projection is first. When a pipe is encountered, the result up to that point is passed to the right hand side of the pipe expression. The pipe expression is evaluated as, and then we use this evaluate function with those rounded brackets. Evaluate, the argument to the left of the comma is people.first. Put in the input data, we get that output, and then this second line down here is what's done by the thing to the right of the pipe. So evaluate, on the left hand side of the column we've got that 0 in square brackets, and we apply it to the output there, and we get back just James. Okay. Okay, so we've now looked at filter expressions, filter projections rather, and pipes, and now we're moving on to something a little different, which is creating a new structure in the result and not just parsing it. So up to this point we've looked at expressions that help to pare down a JSON document into just the elements you're interested in. The next concept, multi-select lists and multi-select hashes, allow you to create JSON elements, create them. So you can create elements that don't exist in a JSON document. Of course, the keys and the values are not novel keys and values. Actually, that's not even true. You can make your own keys. I'm going to call them labels. But the values will, of course, be the same. You have to. You can only work from what you've got in that sense, picking out the values. But when it says here, you can create elements that don't exist in a JSON document. What we mean is, perhaps they're not in square brackets, and now they're in square brackets, or perhaps the values weren't together in one set of curly brackets, and now they are in one set of curly brackets. So they're new elements in that respect. A multi-select list creates a list, and a multi-select hash creates a JSON object. So hash object. We'll go into that in a minute. So here we have a new bit of data. So we've got a people key, and it's an array. We've got 3 people essentially. I don't know why they have a state whose name is up or down or up. Hopefully we're not rotating people, but anyway, there's 3 elements in the array. We're going to do people, square brackets, and then we do dot name, comma, state.name in square brackets. And we're going to get something like that in the result. So we've got an array overall, and there are 3 arrays within that. So we have a list of lists in the result, and the elements in each list are extracted from different key value pairs. You can see A is from name : A in each of the objects. If we look in the result, you can see up, well, that's come from the nested value here. So 3 elements. Just making some observations here. We do have separate lists. Despite that empty square brackets in the query, we haven't flattened everything. Would that be possible? Well, just as a first observation, what would we remove the asterisk from? So far, flattening to me is achieved by removing the asterisk. Well, I can hardly, or it's achieved rather by making the square brackets blank. Well, those square brackets are already blank. How am I can hardly remove name, comma, state.name, because those are my extractors. Name is saying extract from the name key and give me A, and give me B, and give me C. State.name is saying extract from state and then name, which is within its value, and give me up and down and up. So I can hardly remove my extractors to make these square brackets blank. So that's just a superficial point, but it also, just saying why could I achieve flattening with this just betrays a misunderstanding of what's going on. This is a multi-select list, and what a multi-select list is doing is laying out the instructions for creating a list. So I'm saying create a list with name and state.name within it. It just so happens that I'm performing that 3 times. So it's part of the essence of a multi-select list, that it creates a list. So flattening is not possible. It's not coherent to think of that being completely flattened, I don't think. So we have 2 extractors, name and state.name, and we separate those using a comma. How do I know? I'm looking at a multi-select query. How do I know? Is that a multi-select query? No, that's a list projection, remember? That's a slice projection. Straight away I'm thinking, why are they not multi-select queries? Because I've not got any square brackets on the right hand side. I'm not laying out the instructions for creating my lists, or creating my list, the template for a list, and it's just that we printed it out 3 times. In that example we had 3 lists. That's an object projection. Do you recognize that? That is a filter projection. Looks a bit like a multi-select query, that, doesn't it? Because we've got keys within square brackets, but the keys within square brackets are not to the right of a full stop. It's as simple as that. So, and that's our reason. That's what a multi-select query looks like. Okay, but what if we only wanted our one extractor? We only wanted to extract from the name key. So it looked something like that, dot, and then just name. Am I still looking at a multi-select query? Well, you could say no, because there's no longer multiple fields, but you are looking at a select query, we could say. You're still selecting from name and you're putting a template for creating a list. So this is a select query. Is that a projection? No, but why? Projections do have a field after the full stop, that's true, but not a field in square brackets. So this is a multi-select list. We're creating things here. So really it comes down to the fact there are square brackets on the right hand side of the full stop indicating instructions for the creation of a list. It contains more than one field to evaluate, but as we saw, you could just have name. And on the left of the full stop there's a field with square brackets because we're operating on the array. Those square brackets on the left aren't necessarily empty. I've been able to put people1, which means that we focus only on the first element of the people array. Okay. Now this is where the angry man comes in and says, I thought square brackets, empty square brackets meant flatten a list. So let's address him properly now. And that list isn't flat. Well, we never actually even said that empty square brackets mean flatten the list. We said that the asterisk meant that you didn't have a flat list. Remember, removing the asterisk flattens that list. Do you remember that reservation? Stop. and it removes those red square brackets. But then I lost a train of thought there, because that doesn't really work, does it? That means that an empty square brackets do cause flattening, so it's quite hard to square this. But let's think about this. Spot the difference. There must be something that's different between that reservations example, where we have a list of reservations. Within each reservation we have a list of instances, so an array within an array. There must be something between that and our example now with people whose state can have the name of up, down and up. Well, it's true, both of them are an array. People is an array, reservations is an array. Are the elements objects? Yeah, we've got 3 objects and 2 objects there. Is the key's value an array? No, not on the left hand side. So we've just got object, object, object. So thing contained within curly brackets. But we're talking particularly about state, so the value of state is an object. But on the right hand side, the value of instances is an array. And that changes things. And that's why we're able to talk about having square brackets there. Okay, so also remember that when with that reservations.instances.state, blanking the left-hand brackets didn't cause flattening of the list. Now, we might say the rule is therefore if you blank the index expression on the left-hand side of the full stop, then it will not flatten. I mean, that's just stating what happened. We removed that asterisk on the left-hand side of this full stop, and it didn't flatten. Yeah. And so now the angry man doesn't need to be worried, because now it's not true that a blanked out square brackets does cause flattening, because here we had an empty square brackets and that didn't cause flattening. So you could say to the angry man, no, not on the left hand side of the full stop. Okay. Because here, remember, we removed the star, it was on the left hand side of the full stop, that's our sort of test, and it didn't work. So we could say, that's what's happening here. We have got, I'm explaining to the angry man, we have blanked out these square brackets, but they're to the left of the full stop. So that's why it doesn't cause flattening here, just like it didn't here. Okay. But that's not a very good explanation, is it? After all, the square brackets on the right hand side were on the left hand side of a full stop, and when we removed that asterisk, it was effective. Okay, so we can't just, this is to the left of a full stop, so we've got to go a bit deeper than that. That's very superficial, isn't it? So we might say blanking square brackets only prevents an identifier to the right of it from having the things that it identifies from being segregated into separate lists. Okay, so if we blank out instances, it prevents this identifier from having the things it identifies go into separate lists. And that's actually a good explanation for why blanking these square brackets didn't work. Instances is an identifier, and it's to the right of reservations, but it doesn't, it's because it's a projection, it's not finished. Instances doesn't actually pick out anything. Well, it does, but then it's state that actually extracts the states. Okay, so this is how we're understanding it. When you blank some square brackets, it prevents the identifier from the right from having the things that it identifies be put into separate lists. So there's our identifier, state, just to go back to the reservations example. There are our states, which are a part of lists, and they're the values running, stopped, and terminated and running are picked out by that identifier. So this blanked index expression is permitting that identifier to dump all of its values into a single list. With an asterisk, the identifier would still dump all of the same values, but into lots of subcontainers, based on the blanker object the values are extracted from. That's the blanker object, instances. Okay, so that star is, when we move that in, whether it be there or there, well no, not there, it's saying have the right-hand identifier segregate the values it extracts based on, so there's the right-hand identifier based on the blanker object. Okay, so again we bring it in and look at what happens to the result. The asterisk is brought in. Because it's based on the instances, we're going to get running and stopped together in their own little container, and there we do. Okay. Yep, so that's why running is with stopped as opposed to running being with terminated. So when you just look at that and say, oh, is people empty square brackets? I thought empty square brackets meant flatten the list. Well, they do when there's an identifier on the right hand side. Here there isn't an identifier on the right hand side. We've got those instructions for creating our list on the right hand side. In the expression above, the name, comma, state.name portion is a multi-select list. It says to create a list of two elements. The first element is a result of evaluating the name expression against the list element, and the second element is the result of evaluating state.name. Each list element will therefore create a two-element list, and the final result of the entire expression is a list of two-element lists. Now, multi-select lists have a strange property. Unlike a projection, the result of the expression is always included, even if the result is a null. If you change the above expression to people dot, and then the instructions are foo, comma, bar. So those are my extractors now. We want to be looking for foo, evaluate it, take the value. We're looking for the bar key, take the value. Okay. What would happen? Well, each two-element list will be null, null. Okay, so we maintain that structure. The instructions still fire away, it's just that they come back with a structure that doesn't have any content. But we still put that structure in the result. So here we do it, people dot and then foo, comma, bar in the instructions. Now if you look at the data that we're querying, there is no foo at all. It's not just that there's nothing at the foo key or the bar key, there is no foo anywhere or bar anywhere in that list, in that array, which has a list of people. And so the instructions do create a series of lists, a list of lists, null, 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 null. And that tells us something about how it works. Why don't we just get one null, null? Why do we get 3 of them? Because it applies the instructions to every element in the people array. So to remember that, multi-select is meticulous. If we find no key or nothing at the key, we'll still put something in the output, namely null. In the arrays which are created, we want that structure to mirror the selectors. The structure will be maintained. So look, if I've got my instructions here in this query, bang, 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 I'm going to see that in the result, bang, bang, bang. Okay, it's mirrored structure, good. Compare this with a picky projection. Here's our classic projection, James, Jacob, Jaden. If we do people.first, I'm getting back James, Jacob, Jaden. There's no mirroring of structure. The structure on the left is object, 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 object. And I've only got 3 in the output, in the result, because of course the fourth object, if we look on the left, is missing : different. But that doesn't get any representation in the result. So look, if I move first out of my query expression, so let's change the identifier, in other words, off you go, bring in banana, put in the word banana. Now I'm going to refresh it, and the result becomes just an empty square brackets, because of course there is no banana key at all in the left. It doesn't say null, projections are picky. Now a multi-select hash. same idea as a multi-select list, except it creates a hash instead of an array. Well, we're creating instructions for the template of an array, and we're going to print a series of arrays for everything in the object that we're querying. Using the example above, if we instead wanted to create a 2-element hash, a 2-element collection, well, let's see in a minute what is a hash. It's a collection, a 2-element collection that had 2 keys, name and state. We could use this. People. So that's saying I want you to go to the field called people, field key, and we're going to create an array whose elements are objects. That's what that's saying. Whose elements are objects. That is, things encapsulated in curly brackets. And have one key in the object called name and another called state. So I call these labels. They're my labels. And then if I see these red words, that means, and each time extract from the name field and the state field. So the red is where we're extracting from. The name and the state with capital N, capital S, those black words and those curly brackets, they're my labels. Just quickly, actually, I think when we say, at the very beginning, when we say people and then square brackets, that's not saying I want you to go to the field called people and we're going to create an array. That is saying, are we going to create an array? I think it's saying that people is an array. It's not saying we're going to create an array. Well, let's see if we are. Are we creating an array? So, people, dot, they're my label and where I want to extract it from, and we get this. Okay, we are creating an array. Okay. So even though it's called a multi-select hash, where hash is object, it's still putting it within an array. Why is that called a hash in the result? It has square brackets around it, so surely it's an array. There are the square brackets. Well, what is a hash? If we go to json.org, it says JSON is built on 2 structures. That's all it is. A collection. A collection is a collection of name value pairs. In various languages, this is realized as an object, record, struct, dictionary in Python, hash table, keyed list, or associative array. So that's the first thing, a collection of name value pairs, and then an ordered list of values. That's an array. So notice how one name for the collection of name value pairs is a hash table. So perhaps hash is short for hash table. If it is, then what they're saying here is that a hash is a collection of name value pairs. So there's a collection of name value pairs. So there's a hash. There's a collection of name value pairs. There's a collection of name value pairs sealed within curly brackets. So we have 3 hashes there. They're 2-element hashes because they have 2 key value pairs within them, but they're hashes. And the tutorial does agree with that. A multi-select hash has the same basic idea of a multi-select list, except instead creates a hash instead of an array. Well, several hashes. Each hash is an element in an array. Using the same example above, we could, if we instead wanted to create a 2-element hash that had 2 keys, name and state, we could use this. Hash there. There's a hash. And there's a 3rd hash. So the recognizable feature of a multi-select hash is those dot and then the instructions in curly brackets. There they are. These are my labels, names for the fields in the hash we're creating. And just be careful here. After the colon, you might think, after the colon, this is what should the values be. Which keys should we consult to extract the values? And the labels can be anything. We can call the fields whatever we want. So I've put yo, what's up? Appears in the result. Yo, what's up? Design your arrays. So we've now been through filter projections and the meaning of the double equals sign. We clarified how these compound projections are working. If the asterisk could speak, it's saying have that right-hand identifier segregate the values it extracts based on what's to the left. Take its lead from the left. There's a list, MultiSelect list. There's a MultiSelect hash. But both result in lists. Notice that, both result in lists. We talked about the fact that with a MultiSelect list or a MultiSelect hash, because you're designing the result, you get that structure mirrored. Projections, meanwhile, are picky. There's no mirrored structure. And overall, we've moved from queries that parse to queries that create new structures. And there were some terms that I introduced that are a bit idiosyncratic. The blanker object, there's the blanker object, if we're talking about this being the blanker, this asterisk here. And labels, I called these things labels. Okay.